So we started addressing on Monday the last topic of the module, which is the sizing of a reservoir with the main purpose, utilization of the water is production of hydropower electricity. I summarize the fact that stream flow regimes are extremely variable, that normally, in order to size the reservoir, we refer to a reference dry condition associated with a given return period or reliability. The reliability is the probability to have the hydropower plant working at full capacity once designed, right? So reliability of 90% is the probability that the plant works with the design turbine flow. So keeping this in mind and referring just for the sake of examples to a reliability of 80%, so you see here in the slide 1 in 5 year dry conditions, we also have to take into account the fact that normally we cannot use all the inflow to the reservoir because regional norms and regulation state that we have to release an environmental flow, okay? Where this setting is more advanced, normally the environmental flow is seasonal, varies seasonally. So here you have an example, purple line, of an environmental flow that is defined for 4 seasons. 1, 2, 3, and 4. I mimicked the setting that Marche region applies and Emilia-Romagna region applies. So, if your design flow in a reference dry condition is indicated by the red curve here, of course you cannot use all that water, you have to subtract the environmental flow. So the available water that you can use is basically this distance. So the usable flow you obtain subtracting the purple curve from the red curve, and you obtain what I marked here in black, okay? Is it clear what usable flow means? It's the inflow for a reference dry condition subtracted the environmental flow that we have to release downstream in any case. Please look at this little time interval, for example. Here we have a regional norm that sets an environmental flow that is higher relatively to the natural flow we have as an inflow to the reservoir, right? So basically you have to release everything, and the usable flow might go to 0 for some time during the year. Make sense? Very good. So, having this in mind, we can work under 2 working hypotheses. Trying to maximize the turbine flow given the usable volume overall across the year, so that we can select, we can pick the correct turbine to work with the amount of water we have in that stream. Or we have already identified the turbine given a cost analysis. It's associated with the given turbine flow to work at maximum efficiency, and in that case we just size the reservoir accordingly, okay? Right now we will work under the green working hypothesis. So given the usable flow that has this behavior in time, we try to identify the maximum flow we can send to the turbine. Basically, it will be the average flow across the year that at the end of the year sums up to the volume we have usable for the year, right? So basically, if you look at the area under the black curve, this will be a volume. It's the integral of a discharge in time, it will be a volume. That volume is the overall annual volume we have. We look at the average discharge that it's constant across time and produces by the end of the year the same volume. It's basically the green line you see here, okay? So there is part of the year in which the discharge available is above what we need, so basically we would not have to store anything because the usable flow is already higher than the turbine flow. But there is a significant amount of time, the time between these 2 points, in which the available flow is below. So we will store water during periods in which discharge is higher and use it when the discharge instead is lower. This will be the principle behind the sizing. Normally the sizing look at the mass curve. What is the mass curve? The cumulative volume that the reservoir sees as an input or as an output. So instead of discharge, we will look at cumulative volume. This is in time. This is the mass curve. So basically this is what? The integral from 0, when we start looking at the system, 1st of January in all my example, to a given day t, integral of the discharge q. Okay? So basically the black line you see here, it's the integral of the black line we just saw in terms of discharge. There we had volume per unit time. Here we have cumulative volume. So this is a monotonically increasing curve. It cannot go down. Going down would imply the discharge is negative, which it makes no physical sense. So it's a cumulative curve monotonically increasing, and basically this distance from here to 0, it's the available volume overall during the entire year. What's the green line instead? The green line instead is the cumulative volume of the turbine flow, right? And by the end of the year, it sums up exactly to the same overall volume. Okay? Very good. Now, how do we quantify the reservoir capacity? The beauty of this approach is that the approach can be also interpreted graphically. Okay? You take the turbine flow mass curve and you move it down until it becomes tangent to the black line. Then you do the same, shifting the green curve upwards until it becomes tangent to the black line. And the distance between these two enveloping curves is the reservoir capacity. In this example, 22 million cubic meters. Okay? Yes, we'll see this over and over again. What I just said is that you take the mass curve of the turbine flow, the green line, you move it downward until it touches the black line, which is the inflow coming into the reservoir, remove the environmental flow, which we cannot use. Then you do the same upward. You shift upward this curve until it becomes tangent, and the distance between the two is the active capacity of the reservoir. Why? Here we have the two diagrams we were considering. Here we have discharges, and here we have mass curves. So the discharge value here becomes the tangent slope here. The mass curve for the turbine flow, it's a linear curve, right? Because the discharge is constant throughout the year. So volume sum up linearly. whereas the inflow available changes in time. And what you see in this diagram, here, locally, the tangent is proportional to the discharge. The tangents become, the slope of the tangent becomes 0 when the discharge is 0. No volume is summing up because the inflow is 0. Where the curve is flat, it means that your inflow discharge is more or less 0. Okay? So look what we identify with these two tangents. We identify the moments in time in which the usable inflow is equal to the turbine flow. This happens this moment and this moment. Okay? Previous to this moment, the inflow is higher than the turbine flow. Then it becomes lower than the turbine flow. And then again, it becomes higher than the turbine flow. Okay? So we have a situation like this. Here, we have seen a representation in time of discharges, and we have this is a year, okay? Our reference time interval is 1 year. So this is the month of January, this is the month of February, this is the month of December, right? We saw a discharge in times that is something like this. It goes up, then in spring you have normally the maximum, then during summertime you have very low discharges available, and then it goes up again. This is the usable flow. And then we have an average discharge throughout the year. Something like, my drawing is not exactly the same that you see on screen. Let's do something like this. And let's suppose that this is the average flow. The average flow that produces by the end of the year, that produces by the end of the year the same volume, overall volume, okay? Here instead, we have a representation in terms of mass curve, cumulated volumes. Always a representation in time. This is the end of the year. A constant flow, so the turbine flow we want to maintain constant across the year. A constant flow will have a mass curve that will go up, something like this, linearly. And instead, the natural inflow in the reservoir would be something like this. We start with a tangent that is slightly higher than this. Let me add to the blackboard these two vertical references. These are the two instances in which the available and usable inflow equals the turbine flow, right? In these two moments, they are exactly the same. So basically, if you draw the mass curve of the usable inflow, you should obtain something like this. Here the discharge is maximum, so highest slope. Then the slope decreases. It becomes more or less tangent, not more or less. At this time of the year, it's tangent. The tangent is the same of the turbine flow. Then summertime. Summertime implies very limited stream flow availability. Then again, it starts increasing the discharge, and here you will have the same tangent again. Okay? You see it? So what I did is identifying the enveloping curve, the downward and upward enveloping curve that are tangent to the black line in the diagram and to the white line in my drawing here, where the black line has exactly the same slope of the green line in the slide. Okay? Sufficiently clear? Then what we are saying is that the active reservoir capacity is the distance between these two lines. So it is actually the summation of this segment and this segment. Okay? If you sum these two segments, you get the reservoir capacity. Let's see why. So far, so good. Everything I said is clear up to now. So let's see why. Here we have a demonstration. It's really an easy one, which we will go quickly through. Keep in mind that for me, Q in is the inflow that we can use. We already removed the environmental flow, okay? And Q out instead is the turbine flow, the flow we send to the turbine. They are different in time, whereas WT is the water volume stored at that moment in time in the reservoir. So the behavior of this system is fully described by the continuity equation, right? So the inflow, usable inflow, at a given instant minus the outflow that we send to the turbine. Keep in mind that the environmental flow we already released is equal to the variation in time of the volume stored in the reservoir, so the derivative of WV. Okay? So we can separate the two variables. Here we have inflow discharge in time minus outflow discharge, so the discharge that goes to the turbine in time, times dt is equal to the differential of the volume. We can integrate this equation in time and in terms of volume. Between what? Between moment zero, the beginning of the year of the, or the hydrologic year, if we think in hydrological terms. You remember at 1st of October in this hemisphere. Here we're looking at the calendar year. We can integrate that equation between 0 and any given moment in time, t. Okay? If we do that, we have the integral in time of this term. Of course, we know that this is equal to the integral from 0 to t of the available inflow times d tau minus the integral from 0 to t of q out of tau in d tau, and this is equal to the volume stored in the reservoir at time t minus the initial volume, the volume that was present at instant 0, which at the moment we don't know. We don't know what that is, okay? But it's not important. At time t equal to 0, there is some water in the reservoir. We don't know the amount of water. We don't matter. So basically, if you look at the slides, I named WV in the cumulated water volume of the available usable inflow. And the same I did for W out. This is the integral in time of the volume that goes to the turbine. So basically, in my slides, this is W in, and this is all this. I don't know where to write it. All this is W out. Okay? So at any given moment, the volume we have in the reservoir is equal to the initial volume right? The volume we have at any given time, I bring this W0 to the first member, is equal to the volume that was there initially, plus all the volume that got in up to T, minus all the, of course, all the volume that got out at time T. This is just rewriting the continuity equation in integral terms instead of instantaneous terms, right? Okay. So, what are the two most important moments in time here? These two, time A and time B, where the two discharges are the same. You remember, these are the two moments in which the shifted outflow mass curve becomes tangent to the inflow mass curve. So this is TB, this is TA. Any moment previous to TA, the reservoir is receiving more water than what we are using, so the water volume is increasing. Whereas from TA to TB, the water volume is depleting. The volume is going down. And in particular, moment TB is the moment in time in which the water volume will be the lowest, right? Whereas TA is the moment in time in which the water volume will be the maximum. So let's write this equation for instant TA and instant TB. Very easy. It will be the volume initially available plus whatever got in up to TA minus whatever got out up to TA. So W0 plus the blue segment. This. Okay? Now, here we have, instant TA, the reservoir at its maximum capacity. We don't want to over-design the reservoir. Maximum capacity to us means that the reservoir is at its full sizing and the volume equals the active capacity. Okay? Full volume. TB, analogous reasoning. Initial volume plus whatever got in minus whatever got out. Right? So it's W0 minus WB, this segment, minus, meaning that the red WB term there is considered positive. Okay? Is that sufficiently clear? So this is a segment. It has no sign if I'm writing the equation like that. And it's this segment here. Okay? Basically, we have whatever got in, and we're here, and we subtract whatever got out at TB. And the result is a negative term. But if I look at the segment length is positive. So this is why I wrote minus WB. Now, again, we do not want to oversize the reservoir because oversizing the reservoir implies a higher dam implies much higher costs, right? We want the dam to be just as tall as we need, just as high as we need. So, at the moment TB, with the lowest volume, we want the reservoir volume to be 0 in terms of the active capacity, the volume we use for producing electric energy. Maybe there is some volume left for touristic events, but concerning the volume we want to use for producing electricity, it has to be at 0 at that moment. Otherwise, we are oversizing the reservoir, correct? So, Volume in TB is 0. Volume in TA is the reservoir active capacity. We can take the first equation and subtract the second one. And if we do that, we obtain that the reservoir capacity is WA, this segment here, plus WB, this segment here. So, as we wanted to see, the distance between the two enveloping lines. Okay? Is this sufficiently clear? Do you have questions? Very good. So, we work under this hypothesis. We have some usable volume, already considered the environmental flow volume across 1 year, and we want to maximize the turbine flow. But we could also be in a different setting in which the turbine flow we already know. And it's something lower. Look at this example. This is the turbine flow we obtain if we maximize a constant turbine flow across a year which is a reference dry year, okay? So this number here comes from the water availability. The reasoning here is different. We have a set of turbines, and the turbine flow for which the set of turbines is at their full efficiency is just 1 cubic meters per second. So 1 cubic meters per second is proportional to the slope, right? 1.7, 1. We can apply exactly the same reasoning, a graphical identification of the reservoir capacity. We upshift the orange line until it becomes tangent to the black line. And we do it again above. So we identify the two moments in time in which the usable natural flow is 1 cubic meters per second. So any moment before the point where I have my cursor, natural flow is higher than 1 cubic meters per second. We don't need to store anything, right? But then, between this time and this time, inflow is always lower than the turbine flow we want to have, right? So between this time and this time, we need to store water. From this moment onward, we don't need to store water anymore because we have more flow than what we need, right? And so again, the distance between these two enveloping lines is the capacity. Of course, the capacity, if we have a lower turbine flow, is definitely lower than the capacity for using all the available natural stream flow volume. Okay? And the system is not linear, right? 1 is not half of 1.7, but look how the capacity changed. It went from 22 to 11, more or less, so it halved. Ok, you have questions, comments? So, some practical consideration to wrap up this topic. This is a first sizing approach, this graphical approach, because it simplifies a lot the reality. We did not consider evaporation from the reservoir, and if we're not on top of the Alps, we are building a reservoir in Egypt, for example, we might have across 1 year a huge amount of water that leaves for evaporation. If we did not do a good job in terms of assessing the geological unit that are the bed for our reservoir, we might have a significant seepage, water that infiltrates and it's lost, right? So in reality, we need to take into account both of these elements, evaporation and seepage. We can do that using a similar approach, simply reducing the overall volume based on our predictions of evaporation and seepage with the filtration models, right? Another thing I want to underline, this is just a first step sizing. Then, of course, the actual reservoir capacity normally uses simulation. So hydrological models that simulate the behavior for several years, not just looking at the reference dry condition with a reliability of 80% or 90%. Observed stream flow or synthetic stream flow are used as input to the reservoir on the long term to get the final executive sizing of the reservoir. Okay? Do you have questions? Then, in order to apply these concepts, I set up a practical activity in R that we will do together. I need to start a Teams instance. If I recall it correctly, Teams didn't work here. Let's see. Let's see if now situation improved. Since I had to access again to the PC, maybe somebody corrected the issue. Let's see if it works. Maybe so. I'm optimistic. Maybe not. I'm not optimistic anymore. I'm starting to become pessimistic. Meanwhile, here on Virtuale, I'm on the page Practical Activity Reservoir Sizing. There's a folder with the same database we use for the other practical activity on flow duration curve construction and prediction. And there's a script that is basically complete. There are a few steps to develop on our own. Other than that, we will follow steps that are already in the R script as usual. So let's see if I can start this meeting. Everything got back to. So this officially is not working. The online version seems to be working. Okay. View other option, full screen. Okay. Let's see. I'm going to skip the break and perhaps sets you free earlier on, okay? Is that good for you? My glasses. Okay. I need a few moments for Teams to sense that there's some meeting already on. Doesn't seem to be working fine. Let's give it a few moments more. I don't know, it doesn't seem to be sensing the meeting, the ongoing meeting here. Let's have a look at the PDF you can download from the folder. In this practical activity, you will use RStudio to implement the mass curve graphical method to estimate the reservoir storage capacity required to sustain a constant turbine discharge for hydropower generation with an 80% reliability, meaning that our reference condition will be the 1 in 5 year dry condition. You will work with daily stream flow. Meanwhile, here we are finally able to connect. You will work with daily stream flow time series for a selected gauging station and derive representative yearly stream flow regimes. Apply the environmental flow constraint, compute usable discharge, and determine the reservoir capacity from cumulative volumes, that is, mass curves. The assignment is based on the provided R script, which you will complete and run. So here are the objectives. Some of them are already fully implemented in the script. Some of them instead we have to work on. So the implemented part considers, we already seen this, the import and pre-process of stream flows data, the computation of a smoothed stream flow regime. I'm going back here for a moment, meaning that starting from the real stream flow, daily stream flow values, we will compute reference regimes, one for the typical year and one for the dry condition. Median is the typical, and 1 in 5 year dry is our reference condition for 80% reliability. Then we will implement a seasonal E-flow rule. We will derive the usable discharge. Everything is already done. We will construct the mass curve, and then these are the steps to complete. We will evaluate with that method the reservoir active capacity. Then finally, under the same hypothesis, we will evaluate the reservoir active capacity and maximum usable constant turbine flow for a 90% reliability. So if we want to make sure that on average that plant will be working 90% of the time at maximum capacity. Okay? So same assumption for the previous example, complete series, February 29th is discarded. We will use a month, let's say a monthly window to smooth the regime flow. And look at this, this is important, we will adopt an E-flow that is 10%, so 0.1, the average median flow within each period. So from 1st of November all the way to 31st of January is the first season. Then 1st of February, end of March, second season, and so on and so forth. So we will need to understand what the typical stream flow is in this season and then use 10% of it as environmental flow. Environmental flow we will not be able to use, so we will have to subtract from inflows. Maximize a constant turbine flow throughout the year and then identify the usable discharge as Q usable maximum between natural flow minus E flow or zero. When this difference becomes negative, of course, the discharge is zero. Software packages, we need to install an additional package. Open Excel we have. We need to, and you have to install RCPP role that is used for computing moving window averages. And these are all the steps. Only the last one is to be completed. Okay, final task, look at a 90% reliability. So perhaps we can move to the activity itself now. So I will share my screen. I will go to Virtuale. Okay. Virtuale. I will enter our Virtuale resource. I will scroll down all the way down to practical activity reservoir sizing. I'm downloading the zip archive. So under downloads, I have now practical activity. I will store the content of this archive to the usual spot. So desktop, our course, I will create a new folder. And I will copy the content there. Okay? All good? You don't have your laptop today? No.
I thought that we're gonna have the practical activity back.
Okay, well, I am recording. Hopefully Panopto will work. We'll see. So I'm double clicking on the script file. This will open RStudio. Okay. Let me close other things that are open that we don't care for. Okay, this is the script. I want you to notice that there are steps. These steps are the same steps in the PDF document. As always, the script is highly commented, heavily commented. Everything is described, included the variables used in the script itself. Step 8, just comments, because step 8 we need to perform on our own. Backup. this is the description we already read from the PDF. These are the two packages that are needed. So you have to install the second one, and then we have to load them both, 1 and 2. If I look at the packages now, I see that, where is it? RCPP. RCPP is here and it's loaded. Please check this. Open Excel you already have and we already used, so I'm not concerned about that. Is it too...
No, it's fine.
No. Let me increase a bit. 1 click. Okay. So this one needs to be loaded. Do you have it?
Yes.
Were you able to install it? Abdi, you have it? It's installed? If you need to install it, you press here, install, or you follow. You should have a yellow banner asking you if you want to install the package. It's installing. It shouldn't take long because it's just a simple package. We're good? Good. Okay, let me squeeze this again. Now, I uploaded the two packages. This part, it's a part for customization of plots. So in order to have beautiful plots with month names used as labels. So this variable save and stores the day of the beginning of each month. Then the other two are, the other three are instructions to generate thick marks and label for diagrams that we will be opening. Then, this is something new. Lines from 32 to 41. This is a custom function. So a function that we write because it's something we want to use routinely. And the name of this function is circular, it's impossible to pronounce. Circular row mean, okay? I will explain why this is needed after we started addressing the practical activities. For the time being, let me just say that this is a function for smoothing the stream flow regime, computing a moving window average that is k days wide. So the argument you have here, k, is the width in days, 10 days, 30 days, 31, if you recall. 31 days will be the width of the window used for smoothing the stream flow regime, whereas the other argument, x, is the stream flow regime. That might be picky, and using a moving window averaging process, we will smooth the regime. So in order to use customized function, you have to send them to the console. I will select all these lines, all of them, and then I will press Control or Command and Enter. Okay, you will see nothing happening at the console, but if you go to the environment, now you have a new space. You've never seen this function. This is now a function we can use, okay? So when we will be doing moving average, window averaging, we will be using this function. Yes?
What did you press? Control?
I just sent to the console all these lines, all of them.
Yes.
So Control and Enter. And you should see the function under functions. If you see the function under function, it means you can use it. Good? Everything is good? Good. Now, let's check if we have set. It should be like that. If you double click on the script, it should be like that. Let's see if we are here in terms of working directory. So, as always, I write dir, open and close round parentheses. I see exactly the same content, so I'm ready to go. Do you see the same content? 3 files, the PDF, the script, and the Excel file. I just wrote dir, open and close round parentheses. Okay, you have the same files? Good. This is needed in order to set this folder as your working directory. It's something in the earlier classes you'll find also. Good. So the first step is to read in and pre-process input data. So very easy steps, and these are the same we perform in the practical activity on flow duration curve. So I store as n the number of days in a year. Remember that there is no leap year, so every year is 365 days long. Then I will be working on Reno et Prachia. If you remember, Reno et Prachia is the smallest and the one that is the most headwater catchment we have. When we build the reservoir, we normally do that in the mountains, not in the hilly portion, right? So this is why I'm focusing on a very mountainous catchment. Of course, the script can work also for any other catchment, included Reno et Casalecchio, but Casalecchio is in Bologna, so the terrain is already flat. We cannot construct a dam there, okay? Just pointing out this. But the script works anyway. So I'll be working, let me keep track of what I'm sending to the console. I'll be working on Reno et Prachia. Here I'm selecting from the data set the data for Reno et Prachia, lines 46 and 48. 48, these are the data for Reno et Prachia, and I can see that we have 20 years of observation in total, continuous year, right? You remember the structure of this? The code, the site, the year, and then the date. That's the daily stream flow values in cubic meters per second, if you can recall. So basically the data we need are column 1, column 2, column 3, column 4 on stores the stream flow information. The first columns are not stream flow information. Tell me if everything is clear. Tell me if you need any hint from me.
I have a problem with when I put dir, it doesn't give me the other files. But I'm working in the...
No, but it's very easy, and it's good that we see this. So let's suppose let's suppose we are in home directory. We started our studio without double clicking on the script. If we double click on the script, it sets automatically that folder as working directory. But we didn't do that, so our working directory is somewhere else. What can I do now? There are 3 dots. I click the 3 dots. I browse all the way to our folder. practical activity reservoir here, and then I press open. I didn't set the working directory. I'm just looking at the content here, okay? Then there's a gear. I press the gear, and I set as working directory that directory. Set as working directory. Sophia? Okay. So to double check, dir, open and close, I need to see the content. Okay. So basically I ran all the lines up to 48. Then I'm storing the years in this variable. I'm storing the number of years, 20, in this variable. These are all steps that are there for the script to be flexible. You want to launch it with a different catchment, you can. It will work automatically. And then look, I override M with the content of M I'm interested in. Column from 4 to 368. That's the portion of M that includes string flow values. So if I launch this line and I go and check what M's look like now, if you can see the first 3 columns disappeared, went away. I'm ready to start, right? So these are the data I'll be working on, okay? Every year is different from the next one and from the previous one due to climatic reasons. Whereas we will be referring to a reference dry condition for sizing the reservoir and a typical year for identifying the environmental flow. Okay, so we need to distill the stream flow data we have and convert them into smoothed curves that represent what happens in a typical year and what happens in a dry year, okay? Which is very similar to what we've done for flow duration curve. Before we do that, let me save this script, save as. Today is April Foolish Day, 2026, 0401. Did you put a tag on my back? Il 1° d'aprile, il pesce d'aprile, ok. Sì, thanks. But this is not very interesting in reality. So I'm saving this under our shared folder so you can find it later on. So Didactica, here, our academic year, save. So I will be saving this script there so you can find it. I just want to, this is a part that is not there, I want you to visualize the stream flow regime of all these 20 years we have. In order to do that, we use a command we never use. It's called matplot. As always, if you are interested, you go and look at the help online. It plots the columns of a matrix. Do we have 1 year in a column? No. We have it in a row. So we have to remember that it plots the columns of a matrix. All good, Sophia and friends? What are you doing there? You're working like crazy while I'm not doing anything. So there must be something going on. What happened? Tell me.
Nothing. I will close and open.
What?
Maybe I deleted something.
There's also the Control Z.
Yeah, but I already saved it.
Uh-oh. But Control Z still works. You save it, but do undo, undo, undo.
Control Y.
Control Z. Okay.
I will come back.
If you close our studio altogether, Sophia, close even the program, everything, then you go to a folder where you have the original version of my file. You double click on it and you should be able to start. Maybe, or maybe not. So matplot plots the columns of a matrix. Matplot, the arguments are what to use on the horizontal axis. Let's keep it simple. 1 to 365 are the days of the year, right? What to use for the vertical axis? Here we want the stream flows, right? So it's basically M, but M stores a single year on a row, not on a column. So instead of M, we want the transpose of M, which we can obtain using the function T. T is the transpose of a matrix. Then, what else we could put? Type. Type because we want the stream flow regime to be a line. Otherwise, it uses markers and the whole diagram looks like a mess. So the type needs to be L. Then what? We can add, just for clarity, the label for the horizontal axis. This is time in days. And the vertical axis label, which is discharge in cubic meters per second. And then I close the parenthesis. No error sign, so I should be okay. Before launching this, I need to expand this area, otherwise the diagram will not show up correctly. And this is what we get. So basically, any line here, colors are assigned randomly, any line here is a real observed year worth of daily stream flows, okay? There are flood events that can go as high as 50 cubic meters per second, but we are not interested in flood event. As a matter of fact, we don't even produce hydropower when we have a major flood event due to sediment transport, which could damage the turbine. Okay, we're not interested in the volume of water and the discharge associated with large flood events. We are interested in the core amount of water that is always there, that we can rely on, and in particular in dry years. Okay, so from this diagram, remember the scale. This is very important. From this diagram, we will distill the typical year and the dry year. How? Day-wise, remember also what we did for flow duration curves. Annual flow duration curve. Day-wise, we will extract the median, and that will be a representation of the regime for a typical year. Day-wise, we will extract the quantile associated with a probability that is 1 minus the reliability. So in our case, 0.2. Okay? And that would be a representation of our reference dry condition. The diagram, though, will be very picky. Up and down, still there. So in order to smooth it out, we will use a moving average. Okay? And I'll go back to, just quickly, let me know if it's sufficiently clear. I want you to understand, we don't have to look at the syntax of the function. If you're interested, the function is there. You copy and paste it in ChatGPT Copilot. It will explain exactly what it's doing. But I want you to see the rationale of what it's doing. Let's suppose that we extracted the median for each day looking at these 20 years. So each day, day after day, we extracted the stream flow value that exceeds 50% of the observation and is exceeded by 50% of the observation. And we have it. No, I need some more space. Sorry about that. Let's go like this. And we have it in a vector like this. The vector includes 365 components, right? The median discharge here, 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 here. It's still very peaky, and therefore we will use a moving window averaging process. Length in day, K. So we will consider K days, okay? And we will take the average and perform this same operation for the entire vector. What is the problem? The problem is that the number of averages with a K wide window will be 365 minus K plus 1, because I can perform this operation starting from the first value, but then I get to the last value and I need to stop, because if I move forward, I'm missing the days. Okay? So our function, the function I wrote for you, computes a circular moving average. How? It looks at, roughly speaking, half K window here. Okay? So 30 days, it looks at 15 days. It takes this piece and put it right here. Half K. It takes these values and pad the original vector with these values. Then it does exactly the same from the other end. Half K again, roughly speaking. It takes these discharge values and put it right here, in order to be able to have n averages, not n minus k plus 1, but n averages. Circular mean. Circular because it's what we want, it's an average or dry regime, so the end and the beginning must be the same discharge value, and it comes from a circular averaging. Is that sufficiently clear? So basically, red plus orange is again the window we selected. This doesn't look like, but this is again K. Okay? Sufficiently clear? This is the rationale of that function. Want to keep an eye on the time. Good or bad? Let's close and let's squeeze. Okay, step 2, compute stream flow regimes. Here I'm using two names, natural Q, median, so natural stream flow, median, typical year. Circular row mean, the function I just described, we apply it to M looking at margin 2. It means looking at the rows. Margin 1 would be column, margin 2 rows, and what we do is apply, margin 2 is column, so we look at a single column, all the stream flow value, and we compute the median, like we did for flow duration curve. And then we do this for the second column, third column, and so on and so forth. We compute the median of all columns. But we also apply circular row mean with K equal to 31 days. Okay? So we are doing both things at the same time, extracting the median and performing the smoothing. Let's do it. we select a reliability, 80%, we start with that. Then there's the additional assignment in which the reliability will be 90%. So the reliability we select is 1 minus 1 divided by 5 years, okay? Right? So if I compute this, is 80% reliability. This is written for you for the sake of convenience in terms of return period, but it's the same. So this is the reliability we fix, we set. And then again, natural dry condition. Natural dry condition will be the circular roll mean of what? Of the function quantile applied to columns of matrix M with probability 1 minus the reliability. So 1 minus 0.8 is 0.2. Okay? Again, with a window of 31 days. I don't know why I got out, but I don't know if I launched line 59 yet, but I'm doing it now, and I'm launching this too. Then I compute the seasonal E-flows according to the regional regulation. Regional regulation implies that we take the typical year, we get the mean stream flow on the season for the typical year, and then the environmental flow is 10% of it. And here it is, the E-flow computed for the first season, so basically from the first day of the year to the end of January, and then also from November on, if you recall. This is the first season, from November to January. 0.1, 10% of the average of what? This is the typical year, and those are the days we're looking at. So, first of all, I create this vector that is new. I create a new empty vector, a vector full of NAs with length 365. If you see here, now I have a vector that is full of NA, and I start filling this vector with the environmental flow. November and January, so I already see values here. These values are cubic meters per second. Then February, March, then April, June, June, July. Now the E-flow vector is complete. Step 4, compute usable discharge. Do you remember what usable discharge is? I'll go back to the slide. We computed the flow, reference flow, that we have to release. Usable one is the dry reference here minus E-flow, and when the difference is negative, of course, I set it to 0. I cannot use any water in those coming in those months. So back here. Usable Q, natural dry, the reference dry condition, minus E-flow. That's it, very easy. And then line 77, in case some elements are negative, set them to 0. And I have my usable flow. Sorry, I did what Sophia did before. Okay. Usable discharge. Now I have the usable discharge. Step 5, plot the natural stream flow regime and relevant, sorry, there's an error, relevant flows. So relevant flows are, you have a detail in the PDF I passed. The natural stream flow regime for a typical year, the E-flow, the natural stream flow regime for dry condition, and then usable flow. This is longer to say than to see. I'm increasing again the plot space, and I'm launching 1, 2, 3, 4, 5. I'm adding a legend too, so that the diagram is clearer. And this is what we obtained. We have a typical year. This is the median. You remember, big flood events, 50 cubic meters per second. This is instead the amount of water we are interested in, the core of the usable available water. 50 cubic meters per second, not even 1.5 cubic meters per second, okay? But this is water that is typically there, typically available. Do you understand this point? It's very important to size the reservoir on stream flow regimes, not on a single year, because a single year could be very misleading. Okay, so basically, the average of this blue line, the average, so somewhere here, divided by 10 is the environmental flow. The average of this blue line, no, sorry, we have this part, but also this part, okay? Then, the average of this blue line, something like here, divided by 10, E-flow. E-flow, and these are the 4 seasons. Subtracting E-flows from the dry reference condition gives us the dashed black line, which is the usable flow. Okay? Wet season, I release more. Dry season, I have to release less, of course, in terms of environmental flow. And this is why the black line is a bit spiky, no? Due to this step change here and here. That's the way it goes. All good? Sufficiently clear? Good. Let's close this before moving to our studio. Step 6, computation of mass curve. Look, the mass curve is the cumulative sum of usable discharge. That's it. Very easy. There's a function that performs the cumulative summation. So the first value will be the first value, the second value will be the summation of the first and the second, and so on and so forth. Then, of course, we have to apply a units conversion factor, right? In particular, if we want the volume to be in million of cubic meters, right? So every value there, it's a daily average stream flow. So stream flow in cubic meters per second. How many hours do we have in one day? 24. How many seconds we have in one day? 3,600. So 24 times 3,600 is the number of seconds in one day. With this multiplication, we obtain cubic meters. Then we divide it by 1 million, so that we store a mass curve in million of cubic meters. I launch this line and the plot, and this is what obtained. I set the plot to leave some space here, because we are also interested in the differences between the natural cumulated curve and the turbine flow mass curve. And these differences can also be negative. I will plot the differences here. This is why I set the diagram to have some space here, okay? Here I'm adding an horizontal line at 0 so that we keep track where 0 is. We have this reference. Here I'm adding the usual labels to the horizontal axis, and then the second to last step, identify the maximum constant turbine flow. What is this? It's nothing else than the mean on the whole year. It's the mean of the usable flow. Usable flow is this black line. The mean value is the maximum constant discharge we can have throughout the year to send to the turbines. So this will be already in cubic meters per second. It would be, let's see what this is, maximum turbine flow. 0.3 cubic meters per second, 0.34 cubic meters per second. It should be exactly the same as taking the overall volume. Maximum of mass curve is the volume on the very last day of the year, the overall volume, and divided by 365 days, 24 hours in a day, and 3,600 seconds in an hour. Then, of course, we have to multiply by 1 million because volumes were in millions of cubic meters. Let's try to launch only this piece. We obtain exactly the same number. So we did the average in two different ways. Dividing the overall volume by the number of days in a year, or taking the average of the available stream flow. It returns exactly the same. Then the mass curve of the turbine flow I store in this variable. I add the line to the diagram, and if I want the legend to show correctly, maybe I should enlarge. This is the diagram I presented on the slides before. The legend already reports the difference between volume in, at any time volume in is on the black line, and volume out. At any time volume out is on the green line, okay? The difference we are interested in because they set the reservoir capacity. So far so good. Do you have doubts? Good. Very good. This is red. I'm saving it. I hope I'm not saving errors. Step 8. This instead is completely empty. It's for us to complete it. Compute the difference between the two mass curves, volume in minus volume out. So we could name this variable diff. Diff with lowercase d is a function in R, but there is no function in R with uppercase d. Check always this. Do not name variable like R function, otherwise you will not be able to use the function any longer. So the differences for us will be what? Where do we have the volume in? The volume in is this variable, mass curve. So the difference between mass curve and what? Where do we have the volume out? Volume out is hydropower cumulative volume. So HP cumulative volume. Okay? This is the difference. Now, I want to add this to the plot. How can I do that? With the red dashed thin line. How can I do that? Dictate. What do I have to write to add a red dashed line to the plot?
Lines.
Brava, very good. Lines,
Diff.
diff, x values are not necessarily needed, then
Call red.
call equal to red, very good. Then
And WD is the thickness.
what?
And
But thin is the default, so we don't have to specify the thickness. Whereas line type, which should be something like this, I hope I remember it correctly, we write dashed, if it works. Then what else? Thin line, red, dashed. If everything is fine, it should work. Okay, it worked. So we added to the diagram the differences. Now, with the differences, what we are interested in are the highest positive difference. This is WA. Highest possible difference. And the smallest possible difference. It will be negative, but its absolute value will be the segment WB. To get the active reservoir capacity, we simply sum WB to WA. Is it clear for everybody? Do you have any doubt? So I plotted the differences. So the highest difference ever is WA. It's the difference for that instant in which the slope of the black line is parallel, the slope of the tangent to the black line is parallel to the green line. Okay, this is WA. And this, the minimum, will be WB. It will be negative. So let's keep this in mind, that it will be negative. A3, identify maximum and minimum values of diff. Very easy. Max of diff, this is equal to 2. 2 what? 2 what? Units? 2 cubic meters? 2 cubic meters is something like this. 2 millions, which is something different, cubic meters. Very good. And then minimum, whoops. And then minimum of diff. This is equal to minus 0.5 million of cubic meters. This is basically equal to WA. Let's write it like that. And this is basically equal to minus WB. Because WB to us is a segment length, so it's positive by definition. So, the reservoir capacity which we can store could be something like this. Max, as you see there, minus min. Okay, because we have to keep in mind that in this case the differences have signs. Print the result. The interesting results are I was looking, okay. For example, in order to print on screen the result, we could use the function paste that pastes text strings. Paste reservoir active capacity in million of cubic meters and then I leave a space, comma, I'm pasting together this string with what? Round, for example, res, comma, 1. So I will keep just one digit. The reservoir capacity is 2.5 million of cubic meters, and another interesting thing could be to see what is the usable turbine flow. Usable turbine flow in this case, it will be cubic meters per second, comma, round, in this case, I don't remember anymore the name, max turbine flow, okay. Dove sta? Qua. Max turbine flow and digit, I can keep, in this case, 3 digits, okay? Usable turbine flow, 0.345, oh, nice numbers, cubic meters per second, okay? What is left to be done? Compute the hypothetical maximum constant turbine flow and reservoir active capacity for the 1 in 10 year dry condition. So with a reliability which is higher, 90% reliability. It's very easy to do this. We just have to change one bit in the script. But before we do that, I'm asking you, what do you expect? A higher active capacity and a higher turbine flow, a lower turbine flow, a lower capacity, one is higher, the other one is lower. What do you expect for a working hypothesis that considers a reliability of 90%? So a probability that the plant works at its full efficiency 90% of the time. This is the reliability. Higher reliability. What do you expect? The turbine flow to be lower or higher? And the reservoir capacity to be lower or higher?
The turbine flow may be lower and the capacity, no, the opposite, no. If I need to be more reliable,
Be sure. Turbine flow.
Lower.
Lower, that for sure, right?
No.
Yes, of course. Because instead of the 1 in 5 year dry condition, you will look at the 1 in 10 dry condition. Less water, but higher reliability. You're more sure that your plant works longer time with the design discharge. In doing so, you are taking into account a drier year. Drier year means lower discharge. Then, of course, the E-flow doesn't change, because the E-flow, where is it? Okay. Of course, the E-flow doesn't change because it's identifying, looking at a typical year. So the purple line is the same. The red line goes below. The usable flow is even lower, okay? So definitely we should get a lower maximum turbine flow. And what about the reservoir capacity? That also lower. Why? How would you explain that? You change your mind.
Yes.
Hmm. Because basically you will have a black line that will go down and will be more squeezed. And since you are interested in the difference between the highs and the lows, if your black line becomes more squeezed, the difference also will decrease. Okay? Let's check our hypothesis using Galileo's empirical approach to science. So, the only thing I have to do is, I don't know, if I show you then it's too easy, you have to do the same. No, I was being silly. If I find the window, I'll show you. But no window. No window because, okay. No preview, the window is there. So the only thing I need to change is the reliability level. I want 1 in 10, so 1 in 10, which means a reliability of 0.9. And then what I have to do simply is to launch all, some of them are not actually useful. We should have skipped them, but it's much easier to launch everything. Keep the result in mind, 2.5, 0.3, 1.8, 0.26. So we were correct on both sides. Okay? Difference are smaller than before because the whole black curve went down and squeezed. As a result, also the active capacity is smaller. So I might decide to have a larger capacity, a higher turbine flow when the plant works at full efficiency, but a longer period of time in which I expect the plant not to be working at full efficiency. This is a cost, okay? Or I can spend less and produce less hydropower because, of course, if the turbine flow is lower, I produce less hydropower electricity. So I have a lower gain, but I have also a lower cost because I have to build a smaller dam. These are the elements to consider in order to find an optimal solution that works fine for you, the stakeholder, and the water managers. Is the practical activity sufficiently clear? Good. So, this could be the end of the module, but if you want, I'd be happy to meet you after the Easter break to wrap up the module and also provide you with the survey on teaching quality, which is something very important because this is the first year the module has this shape and this content, so I need to get your feedback on my clarity and on the things we studied and done together. So if you are okay with it, if the room is empty, let me know today. But if you are happy to meet next Wednesday, I wish you all a great Easter break, and I'll see you on Wednesday for a wrap-up of the module, all the topics. I recall also how exams are performed, and then the teaching quality survey. Yes,
I will not be present.
okay.
So
But I will ask you in any case to fill the teaching quality survey. Okay, it's very important for me. So I will chase you all. I want to see 9 forms filled. Nine, I think. Okay, good. Well, 9, I don't know because you join halfway through, so it's up to you.
No, but thanks for the recording.
Ah, right.
Yeah, we have all the classes.
Okay. You have questions? No? Happy Easter break.
small.